All right, everybody, we're starting chapter 6 today. Chapter 6 is on discrete probability distributions. This is Math 21. What was it? Day 12, lecture day 10. And the section we're doing today is on just discrete random values in general. Now, does anyone remember from the beginning of the semester, we were talking about quantitative data, and there was two forms. One was discrete and one was, what was the other category? Continuous. Continuous is chapter 7. So we're hitting discrete options. This chapter 7, will be continuous. We'll hit both categories. Excellent memory. I think what you're going to care about, let's just put it right at the start of the paper, where you're going to use this. The things you need to know is the equation expected value is something you need to know. And they use E of X for it. And that is the sum of X times P of X. And you'll see that today. Stat Crunch, what we're going to do in Stat Crunch is stats, calculators, custom. And custom is at the bottom of the list. So, random variables. We talked about discrete stuff, but what are random variables? Random variables are numerical measures of the outcome from a probability experiment. Get a haircut? Yeah. Looks good. Yeah, thanks. Like we were talking about probability experiments in chapter 5. Here we're going to go into specific ones. We will use, and it's really fucking hard to distinguish, a capital X. I'll try to use like Roman numeral X while I'm doing this, so it makes it stand out a little bit better. But like on the homework and shit, you just got to look for the size difference. Capital X is usually the category of outcomes. Bless you. And lowercase x is all possible numerical values for x. I don't know what you're eating, but when you held it up a second ago, I thought it was a giant fucking like Capri Sun. I'm like, God damn, why are they, when did they start making Capri Suns? Because I couldn't see the food. You're just holding it like you were like drinking from something. I'm like, and she's got a fucking bottle. She's like double fucking fisting the drinks. And then I saw you bite. I'm like, shit, she's fucking eating the Capri Sun. That's when it clicked that I was an idiot. All right, so let's give an example you all fucking know. Has anyone in here never played rock, paper, scissors? If you've never played rock, paper, scissors, your parents need to be fucking slapped. Because like that's like a go-to game. It's free. You need it. It's a way of settling disputes. It's something every child should have learned. Rock, paper, scissors. Or the improved form, rock, paper, scissors, lizard, spock. But that's for nerds. We'll stick with rock, paper, scissors. Let's say we're going to go best of 5 games. And I don't give a shit how many times you win. I give a shit how many times I win. So capital X is going to measure how many wins I have. What are the possible numerical outcomes of that experiment if we do best of 5? And we play all 5. Not like whoever gets the first 3 is done and then quit. Like if I play we'll play all 5. How many wins can I get? This shouldn't be an overwhelmingly hard question. Someone answer me.
5.
I can get 5. Anything else I can get?
0.
I can get 0. I can get 4. 3, 2, 1. Not the order I would have put them in, but that's the order I heard them in. And so that's what we'll do. So that's what I mean by big X and little x. So then we could measure what is the probability that big X equals a specific X. Like, what's the probability I win 3 or more games? Maybe we'll do A, exactly 3 games. And B, at least 3 games. Exactly 3 games is usually, like if you were to play in real life, that's the good shit. It usually means each got 2 on the first 2 games. You're in like the end of the World Series. We're not going to calculate this right now, but I'm showing that how the notation is set up. So this would be probability that big X equals 3. And this would be the probability that big X is greater than or equal to 3. Does this notation make sense? Does it help having like an example? I think it's kind of clear. Once you know what like the category is, I don't want to write probability. I didn't want to write like how many wins I have. That makes a really big parentheses. So we just use an X and we define it up somewhere else. So I could plug any of these numbers in here. I can figure out what's the odds of or probability of me winning 0 games. What's the probability of me winning all 5? So how many games I win is an unknown quantity. That's my X. And that's my random variable. We say it's random because we don't know what's going to happen. I'm going to use RB from now on for random variable because we say it enough in this fucking class that like you're going to get tired of writing out random variable yourself. This was a discrete probability model. Because my responses were countable numbers. My only outcomes were countable numbers. Can't win 1.3 games. That's fucking stupid. I could have an average win of 1.3 games, which means I suck at rock, paper, scissors, or fucking really unlucky. When we have infinite outcomes, like we can have decimals. That ends up being a continuous random variable. And that's chapter 7, as I said a little bit ago. Let's, and we care a lot about mean of stuff in here. So the mean of a discrete random variable and I fucking wrote out random variable again because I'm a sucker. Well, if we have a actual data, like we got a big summary or a big bunch of answers, a whole lot of answers, individual responses, we would have an X bar and we would just calculate normally, like using, you add them up, divide by the total. And what I mean by actual data, I want to make it clear, is each individual response. Felt kind of bad yesterday in the afternoon. I have an algebra class, and they are very interactive group. They very like they talk more with me than any other class I probably ever had. And there's some folks that like to one up each other. Like, I got the answer right. Did you get it right? And so they started like heckling each other. And rather than settling it down, I started instigating. Which was fine until I started participating too much. And when someone didn't answer, I'm like, what, you're a chicken? Don't want to answer? And he didn't care. I know he didn't care because he's one of the ones, he's come to me, he's talking to me after class. But telling a student they're a chicken for not responding in front of a bunch of other people that never talk is one hell of a way to make sure they don't ever fucking talk. Like, that was dumb. I need to, like, when class comes, I apologize to him already. I need to apologize to him in front of the class saying, it's okay to not answer.
You're gonna start it.
Oh, yeah, I was fanning the flames on that shit. It was good times. If we have a summary of the data, like we added up the responses. This is where we use B of X, and that's our expected value. Summation of X times P of X. And we call that E of X. And the reason why they call it its expected value is we call this the expected value because this is theoretical. But if we do the experiment enough, this is the value we expect for our mean from a sample. Like the law of large numbers. We did law of large numbers, remember past the pigs? And we added one more pig and it didn't really change the probability. It's that kind of idea, but now we're not having a pig, we're having numbers. You add one more of a number category, it doesn't change it much. I need to pause and leave that up there for a little bit. This is a expected value is a huge term in the casino industry. Because expected value is all about your point of view. The casino has a positive expected value. Players have a negative expected value in the casino. Well, the mathematical definition, they have a negative expected value. No one walks into the casino thinking, I'm gonna lose. Well, no, they do, but they're like, hopefully I don't lose. There are some people that are like, I'm not gonna lose. And they will fucking lose like 20 times and then win once. And the one win might offset like 10 of the losses. It might be a big win, but they're still way in the hole. And all they ever remember is that one fucking win. This is my wife's fucking family. Her entire, like, not all of them, most of them, damn near degenerate gamblers. Well, not so much anymore. They like to gamble. Like it was like bingo was the thing for her. I'd go and we go to the, she and her family always went to bingo, like at Eagle Mountain, Table Mountain, or Lemoore, Catchy. And then as soon as bingo was over, they go hit the casino, the slots. And several of her family members were like, nope, I remember I won thousands. Yeah, I mean, you've lost like tens of thousands. All right. Degenerate's probably a little strong of a word. But let's look at some examples of this. Does anyone need that up longer before I start yanking the shit away? All right, so this was like This is pre-pandemic, as you'll see in a second. The number of movies streamed on Netflix. Number of movies people streamed on Netflix in a month. Why don't you hear conspiracies of fucking like Netflix and Hulu fucking spreading the fucking pandemic? Because they came out like cash fucking cows. That was fucking like make that motherfucker rain every goddamn day. Dollars just raining on you. Everybody's stuck at home. They want some entertainment. You're at home and you're paying $9.90 a month, $10 a month to be entertained, fucking 20 hours a day.
Did you hear about Netflix isn't like allowing you to like share your password anymore?
Yeah, I've seen that they're like trying to restrict it. You could try. All right, so here's a table of the responses. So that's like the number of movies watched. We'll call that X. And the proportion that they watched it, well, like this is big X equals X. So the probability that people watch 0, this is just a summary. This was 0.06. The probability that a household watched just 1 was 0.58. Probability that a household just watched 2 was 0.22. Probability that a household watched 3 was 0.10. Probability that a household watched 4 starts tapering off. And probability that X equals 5 movies is 0.01. Not very high. What do those add up to? What does this column add up to? What? Close. 1. Even if you don't get out a calculator, that should equal 1, which is 100%. Remember, that was one of our 2 requirements for a probability model. Just a reminder, probabilities had to be between 0 and 1. All of these are. And the sum of the probabilities had to equal 1. So that's what my big E means, sum, as a reminder. Well, let's figure out what our expected value is. Our expected value is the sum of X times P of X. So I'm going to multiply the stuff from the first 2 columns. You know what? There's a lot of shit here going on here. I'm going to put a little dotted line after every 2, so it makes it easier to like follow. I have X is 0 times the probability times 0.06, which is 0. And then I have 1 times 0.58, the probability of getting a 1 is 0.58. Probably getting a 2 is 0.22. I multiply those together, I get 0.44. Probability of getting a 3. .30. Probably getting a 4 is 0.03. We multiply that by 4, we get 0.12. And 5 was only 0.01. That's like how much is 5 pennies? That's 5 cents. What does that column add up to now? I'm going to use Stat Crunch at some point in this class. Might as well get it open. You want to add that up? 0.49. That is our mean or our expected value. Now, if I tried to draw a little histogram by hand, let's see, let's do a histogram by hand. 0, 1, 2, 3, 4, and 5. Let's make that 0.6. So halfway is 0.3, 0.45, 0.15. I got 0 probability of a 0, which seems really fucking low, right? They basically got no one to say, we watched any movies. Did I say? Not 0.0, 0.06. I done, yeah, the probability was 0.06, which is low. 0.58, look at this motherfucker, way up here. Zero 0.44 or 0.22. 0.10, 0.03, and 0.01. So like if I fill this in, make it a little easier to see. What kind of graph is that?
Bell shape? No.
Left. Right.
Who thinks it's bell shaped? Who thinks it's skewed left? Raise your hand proud. Don't fucking be all. Who thinks it's skewed right? The skew is where the longest tail is from. So it's the longer tail is on the right. This is definitely skewed right. And the mean is always to the side of the tail. So getting like a 1.49 is like over here somewhere. So that's like our mean. And it's not directly in the center of the hump, it's to a little bit to the right of the center of the hump. Let me put these values in StatCrunch and see what we get there. So I'll just write it X and P of X right now. Columns, that way now I know what I'm getting. 0, 1, 2, 3, 4, 5. Yeah, 0.06, 0.58, 0.22, 0.1, 0.03, and 0.01. We are going to go stats, table, stats, calculators, and custom is way down at the bottom. Notice everything else on this motherfucking list is alphabetical, except the word custom. Like, who the fuck did this? They just need to get slapped. All right, so weights are your probabilities. So values are X's and weights are P of X's. That's important to know. When you're doing this in StatCrunch, values are X's and weights are P of X's. You don't need to put anywhere or anything like that. You just click compute. Look at that. They draw the fucking histogram for us. Notice what this thing has. It gives us our mean. It says the mean. It gives us a standard deviation. And right now it says probability X is less than or equal to 1. And the 0 and the 1 columns are highlighted in red. So it like gives me a visual representation of what this bottom probability is. And it actually adds up the values for us. We have drop-down menu. I could just find out exactly what 1 is. We already know it's from the table. It's 0.58. But setting equals to 1 does it. I could say greater than 1, which doesn't include 1, but includes 2, 3, 4, and 5. And you may not be able to see it well in the classroom, but those are all red right here. If you're on your laptop doing homework, you'll see that you can see which ones they're talking about. So if you look for the red on this, it'll tell you which columns are actually counting up. And they got 0.36. And they were counting up these right here. If you add those up, you get 0.36. So it's kind of neat. Custom calculator's got a lot of cool, fun gadgets on it. But I want to make a quick note there. The custom calculator, I said it out loud, but I think having it written somewhere helps. Your values are your X, and your weights are your P of X. Bullshit, right? Ooh, another one I need to load on the big screen. Roulette. Oh. The next example I'm going to cover with you involves calculating the expected value for roulette. So I think showing you what roulette is first. If you've never played it, good chance you haven't if you're under 21.
Oh, this game.
Yeah. So at a casino, they have this little table. It's got a dish. It's a wheel. It fucking spins. And it spins one direction perpetually. And when they start the game, they flick a marble the opposite direction. So the marble eventually is going against the spin, eventually slows down and falls in the center. And in the center is a bunch of slots, like you can see right here. There's a bunch of slots and there's numbers associated with the slots. Half the numbers are red, half the numbers are black. Except some cases, there's green slots. Some tables have just one green slot and it's called 0. And that's like the high rollers table. Casino prefers this one right here. Let me find a better fucking view of it. Nope, that's not a better view. Why is there a bunch, no fucking good views of the double one? There used to be. A lot of single 0 ones.
You know, type double roulette.
Really? Fuck off. There we go. I guess we'll just use that. So there's 0 and double 0. And so you can bet on any particular number. You can bet on, put your like coin, your chip between 2 numbers. You can put it on a corner and bet on 4 numbers. You can put it on any of these that say first, second, or third 12, and it does the entire group. You can bet on an entire row. You can bet on first half 1 to 18, second half 19 to 18, odd or even, or red and black. Notice that some of the odds are red and some of the odds are black. So like, it's kind of like a mix up of what's what. And then 0 and double 0, or ought and double ought, they're called, are green. And the probabilities you get for payoff for each of them is calculated a little bit differently. The big money comes from betting on a single number and having it hit, but it doesn't hardly ever happen. It happens 1 out of 38 times. So let's look at probability forward line. It's a fun game. You can play. Your money goes slowly. It's very suspenseful. There are 38 numbers. I just showed this all to you pictorially. We have 0, double 0, and then 1 to 36. Half are red, half are black. Half are odd, half are even, excluding the zeros. The way they calculate the payout, so they calculate the payout based on no zeros. Like the table has no zeros. So let's look at getting a specific number, say 13. There are 36 numbers and only one outcome that's favorable, not including the actual 0 and double 0. The payout is in terms of odds, 35 to 1. These are called the odds. And so how the odds convert to probability. This means 35 against and 1 in favor. Which means a total of 36 outcomes. 35 plus 1. So that's where the 1 in 36 comes from. 1 favorable over 36. It's just a brief lecture on what odds to, because a lot of people don't understand how odds work, what it really means. So like, if I had 3 to 2, another way they write this is 3:2. Means 3 against, 2 in favor. So total of 5 outcomes. Which means you have a 2 in 5 chance, 2 in 5 probability. That's how you work with odds. So if you're ever in a casino, that's, I don't think there's any questions in the homework that have it. But like if you ever do casinos and they talk in odds all the time. That's what they give a shit about. Let's show you what the payout, or let's do this expected value for roulette. And we'll do a specific number. We need an X column and we need a P of X column. So what goes in here? I'm going to put in here like, we need to think about how this column works because these got to be numbers. So like, what are the outcomes here? Of you betting. You can either hit your number or you can miss your number. And we had 35 to 1 odds. Which means if I hit, I win $35 for every dollar I bet. Plus $35. If I lose, I only lose $1. Some tables will allow you to play as low as $1. Anything higher is just multiplying these numbers. The actual probability of hitting the number, though, there is the 36 numbers plus the 2 green numbers. There is only a 1 in 38 chance of that happening. Which means there is a 37 out of 38 chance of losing $1. So If I multiply this, I got X times P of X. This ends up being plus 35 over 38. And this ends up being minus 37 over 38. And that's not very helpful for us. Like we want to think in terms of money, because we were talking about money. This is approximately 0.0263. And this is, nope, sorry, that's an individual. Fuck. I'm going to write it above it. So 1 over 38 is approximately 0.0263. When I multiply by 35, this top one to 2 decimal places is 0.92. This bottom one to 2 decimal places is negative 0.97. So my expected value, I add those up. 0.92 plus negative 0.97, and I get minus 0.05. Negative a nickel. Notice I can't lose a nickel on any specific bet. I can either lose $1 or I can win $35. So this is the long-term expectation of a player's gains for each dollar they bet. It's negative, which means you will lose a nickel on average for every dollar bet. That doesn't seem so bad. I can win 35 bucks and I might on average lose a nickel. I could play a couple bets and come out pretty good. The problem is, good chances are you're not going to come out ahead, and nobody plays just 1 or 2 times. And no one plays for $1. You don't go all the way to Vegas to play for a fucking $1. So like this isn't very much, like this means, so the opposite this means the house gains a nickel for every dollar bet. Which isn't a lot. But those roulette tables are fucking constantly in play. And they probably get, it's probably 3 to 5 minutes between each spin. They gotta have time to pay out bets, take in all the lost bets, give time for people to lay down new bets, make sure everybody's like ready, and then fucking spin that motherfucker, let the ball settle. And it takes 3 to 5 minutes. So they can get between 10 and 20 play the games an hour. And like you can easily get like $10 million bet over a day. Not from any one player, but from all the people. from everyone. That might be high. But definitely 10 million in a month. 10 million times 0.05. Is $50,000. Is that enough? No, it's 500,000, isn't it? 10. Yeah, $500,000. All of a sudden, we're talking about raking in some serious ducats. That I'm kind of curious. I know people at the casino industry. I'd ask. Like I know people that work up at Chuck Chansey. My friend, he works up there. He's a pit manager, and I've calculated the progressive jackpots for the card games at like Club Matrix in San Jose. They've paid me a lot of money to do their calculations. I know the managers. I bet I could ask how much money is bet on a roulette table each day, and they could tell me. If they have roulette, it's a California. I don't know they have roulette in California, like unless it's an Indian casino, and they're not an Indian casino. They might not have it. All right, so that's roulette. And funny thing is, doesn't matter which way you think you bet on. You could bet on odd or even, which is 2-1. You can bet on red or black, which is 2-1. You can bet on any of the rows, the columns, every fucking call, every way you could possibly bet on a table that has 2 zeros is a negative nickel per dollar, which is neat. The expected value, regardless of what bet you make, is the fucking same. It blew my mind until I did the math on it, because in my head, like, you're gonna lose the fucking single bet all the goddamn time. If I bet on 13, I guarantee that motherfucker will never hit while I sit there. And as soon as I walk away from that goddamn table, I will hear the fucking caller say 13 as soon as I walk away. I'll never hit. But so I play red or black or odd or even, and I used to play it for a long time. Like I have almost 50-50 odds, almost. But the expected value is the same. I'm still isn't the same as doing the big bet. Your real best way to play roulette, if you're gonna do it, is just play one fucking spin and play everything you're gonna bet. And pick something that has fucking reasonable payout. Like the odd or even or red or black. You'll double your money like 47% of the time or something like that. Every time, every game you play compounds how much you lose. All right, one more scenario and then we'll be done. Term life insurance policy. So, coverage for a lady in a specific age group. They have all sorts of fucking custom markers on how shit works. How old you are, whether you smoke, whether you know, all sorts of shit. So whatever her group is, she pays $530 a year. For $250,000 in coverage. Now, it doesn't make a lot of sense to calculate her expected value, because if she loses, she's dead and she don't give a shit. So, like, let's calculate expected value for the company. Oh, I need to give you a probability. Probability of survival is 0.99791. What are the outcomes of this? There's only two possible outcomes of this thing over a year. From the insurance company's point of view. What are they? Not numerically, just like think like big picture. What possible ways outcomes affect the insurance company? Anybody? She lives or she dies. Those are the only things that fucking they're concerned about. It's a life insurance company. You're paying life insurance. It's not health insurance. It's life insurance. You only pay out if they die. Right? That's the only fucking concern. They're not in it for your welfare. They're in it to make money. It's a business. Having the life insurance benefits your family. If she lives, the company collects $530. And the probability of her living was given. 99791. If she dies, they have to pay out $250. But they've already collected $530. So their net loss is negative 249, 470. What's the probability of her dying? It doesn't say, does it? Can we figure it out? How can we figure it out? A probability model always has to add up to 1. I know this column right here has to add up to 1 when I'm done. So this entry here must be 1 minus 0.99791. This matches up with our probability of E complement equals 1 minus probability of E. When E is survival, the complement of survival is not surviving, right? And not surviving means you're dying. So if you calculate that out, you're going to get 0.00209. If I multiply this over, x times p of x, 530 times that is $528.89. The 2 decimal places. Since we're talking money, we're just gonna do 2 decimal places. If you multiply out dying, you get negative 521 and 39 cents. My expected value is if I add those up and you get $7.50. This means in the big picture, they only make $7.50 per policy a year. But they don't just have one policy. Insurance companies offer policies to millions of people. So just 1 million policies? 1 million times 700 or $7.50 is $7.5 million a year. So the small expected value is never a lot. It's what happens in the big picture over many, many operations. They don't make a lot per policy, but they have a fucking metric ton of them. A fuck ton of policies. All right, that'll be it for 6.1. Call it a wrap, and I will bid you adieu. You can GTF up. Have a good week.